Hello, everyone. Thank you for tuning in. My name is Professor Leora Dresselhaus-Marais, Stanford University, and I will be teaching you today about an introduction to shock compression of solid materials. This workshop is part of a larger series of workshops by the Kamsky Center for Additively Manufactured Complex Systems under Extremes, where we study these types of shock compression and other types of compression in additively manufactured, interesting metallic systems. So to start off with, we can ask ourselves the broader question of where exactly do we find shock waves in the world around us? Well, to answer this, we can first look at perhaps the most dramatic of conditions, where when two planets collide with each other or a moon collides with a planet, we find this launches an incredible shock wave that can dramatically change the composition and mineralogy of both planets involved. In fact, there are even theories of how the moon formed that involve this type of shock compression. In other systems, for example in aerospace, when we have vehicles that cross the sound barrier, we find that in order to understand how to build those aircrafts or spacecrafts out of the appropriate materials to withstand the conditions around them, or how to build, the construction materials for houses that are underneath these types of supersonic jets, we need to understand how that shock wave is interacting with the material itself, either causing it to fail or hopefully not to fail. In yet other systems, we find, for example, when explosives or weapons fire, that this launches what's called a bow shock on the air surrounding it, or the projectile, that ultimately can cause immense harm to biological systems and humans, as well as the surrounding environment that we hopefully want to protect even under certain circumstances. So in all of these and yet many, many more applications, including, for example, applications of extreme weather events where we have rocks flying into buildings during hurricanes or during tornadoes, we need to be able to understand the basic materials physics that govern how these shock waves interact with materials and how those manifest in protective or catastrophic failure. To understand shocks, we can start with perhaps one of the more relatable versions of these systems, starting with a classical sound wave. So a sound wave, as some of you may be familiar with, is a wave that propagates through the air surrounding us, or through the particle materials that surround us. If we have, say, a transducer like this gray material here, then as the transducer is vibrating at some characteristic frequency, it perturbs the atoms and particles that are near that transducer layer. This ultimately launches a wave of varying density that then transports and oscillates as it transports, carrying sound based on, or the timbre of the sound based on the frequency at which the wave is propagating. So, of course, for a sound wave to really exist, we need a pressure wave in the material to effectively describe the force per unit area that's describing this push, and this needs to be oscillatory in time. We also need this to be pretty close to the equilibrium position of these materials, or the atoms need to be pretty close to their equilibrium positions. Otherwise, we would see some pretty unusual types of effects here, i.e., we wouldn't really see oscillations. So when we ask ourselves, well, what exactly is the speed of sound, we find that the speed of sound is equal to the square root of the modulus divided by the density. So, of course, as we start making these sound waves louder and louder, eventually what we find is that the atoms get further and further from their equilibrium positions. This means that the density starts to change and increase, but also that the modulus increases much faster as it is determined by things like the speed of sound and, as it is determined by the interactions between atoms. So ultimately, what we find is that under high enough or loud enough conditions, we end up with the high enough amplitude sound waves actually changing the material itself and its own inherent velocity. When we look at how this manifests, we can see that our initial sound waves with this oscillatory shape to them that's propagating in space very quickly transforms to something that looks a little bit more like this, where effectively we now have all of the highest amplitude pieces of this wave shifting to the very, very front of the wave, creating this discontinuous front that is the leading edge of our shock. Then all of the highest amplitude pieces are together, defining what is called the stable region of a shock wave, or stable compression state. And then following that, we get release and subsequently rarefaction to negative pressure, before eventually we subside to our ambient conditions. Although it might seem like we could just map our sound wave components onto our shock wave states, indeed it turns out that this is a nonlinear process and that therefore simple, addition doesn't quite work the way we might hope. Indeed, beyond just looking at this as a pressure profile, we find that with pressure comes a lot of temperature. As soon as we have this nearly instantaneous jump from our lowest to highest pressure, we ultimately have a ton of kinetic energy that we've generated that now has to go somewhere. And so it thermalizes, generating a commensurate thermal wave that propagates with our mechanical wave and ultimately defines a series of states that we can categorize or classify based on the equations of state that we'll derive in a few slides. Similarly, it's important to understand that the duration of this stable shock wave is incredibly important to understanding the material response that ultimately happens. If we end up with no duration of stable shock and it decays immediately, that's called a decaying shock. And that ends up with quite different properties than a stable shock, which in itself is different based on the duration of the stable shock, from nanoseconds to microseconds in some cases. So when we launch a shock wave, typically we try to launch a shock wave in a way that allows us to consider the shock not as a complex shape, but instead as a nearly planar mechanical wave that propagates along a linear direction of propagation we can define along one axis. So largely, when we generate shock waves, we try to generate them in such a large region. The regions that we probe are nearly planar, or have a nearly planar shock response across the region of interest we're sampling. This means that as the shock wave is traversing the material, its shape in terms of pressure versus time evolves in a nearly uniform type of a profile. Although we'll see in a few slides that it actually isn't completely uniform when we look at solids that interact with the material itself, or with the shock itself. So to define the behavior of these shock waves, we need, as I mentioned, an equation of state to be able to understand how these jump conditions at the very, very beginning set the dynamics that follow and the states that follow at very extreme pressure and temperature types of conditions. So we're going to start by defining our system, the green material here. We're going to say that we are this human right here in red that is in a stationary frame of reference, meaning that we are at rest and all the particles around us, at least initially, are also at rest. We then can define a shock wave that is propagating at some velocity defined by capital U, and we're going to define the shock front as propagating in this direction. And we can say that our initial conditions are defined by the pressure, density, volume, temperature, and particle velocity that we initially live at in the rest frame of reference. which, as I mentioned before, we often would assume is no particle motion, ambient conditions. But following the shock wave, we know that we end up with a lot of pressure and temperature that have been generated, and in fact, this also does quite a bit to distort the velocity, the particle velocity of the materials, so the speed at which each of the atoms are moving in the material, the density, the volume, and the temperature. So now that we have that view of our frame of reference and the shock jump conditions, we can now define the continuity equations across this jump. So first off, we know that we must follow Newton's law. Mass must be conserved across this shock front. We can quantify this based on the density times the particle velocity, effectively showing us density times the mass flux. Similarly, just to finish that up, we know that before and after our shock wave, we haven't created material. Similarly, momentum must be conserved, which takes the form shown here, where now we know that our initial momentum must be the same as our final momentum, which translates to a change in the pressure, particle velocity, and density that describe our system. And finally, we understand that energy must also be conserved, which we can express in this way using some of the equations from fluid dynamics. I'll note that what we've been using so far as capital U to describe our shock front is usually classified in shock physics as U sub s, which is called the shock velocity, whereas the particle velocity, lowercase u sub p, is defined as the post-shock minus the pre-shock particle velocities. So from the conservation equations that we just saw in the previous slide of mass, momentum, and energy, we can now relate the state variables using these equations here that give us now the relationship between the pressure, volume, and internal energy, that's specific volume and specific internal energy, to be able to now describe all of these shock parameters based on the shock velocity and the particle velocity before and after the jump. So this is important because these velocities are actually measurable and therefore allow us, as well as the density, and at least the initial density, meaning that it gives us now the ability to take observable quantities and use those to now get access to an understanding of the thermodynamic quantities required to now describe our system. So from this, we ultimately now can describe what is called the Rankine-Hugoniot relations, which take this form that effectively describe the locus of points, each of which describe one single shock wave based on an initial set of starting conditions, all possible ending conditions that describe the jump conditions as we've discussed on the past few slides. So it's important to note that no 2 points along the Hugoniot can be reached from each other, as from any given point on the Hugoniot, you no longer have the same initial conditions that you had in this particular one. When we start from the initial conditions at rest, this is called the principal Hugoniot. So the principal Hugoniot, in this case, we're calling that P0 and V0 being the ambient conditions. We can describe the relationship between any point on the Hugoniot and the initial conditions using what's called the Rayleigh line. So the Rayleigh line has a slope that is equivalent to the shock impedance we'll see in a few slides that tells us things about the shock response that we're studying. Similarly, we can plot not just the information about the jump conditions, but also the release of that pressure, which takes the form of an isentrope shown by these lines with the S's here. So that's constant entropy, compression or decompression. So this allows us to now understand both the loading and unloading types of pathways. It's worth noting now that none of these equations that we've considered so far explicitly include a consideration of temperature across that shock front. This is incredibly important, and one of the reasons why a large question across shock physics asks, what exactly is our understanding of temperature, and how does our understanding of the material change the way that temperature should evolve during these shock responses? As we can see, for example, in different types of material failure modes that give rise to very different types of heating effects that can be quantified in some cases by the Taylor-Quinney factor. We'll see that towards the end of the presentation. Similarly, it's important to understand that a shock wave also obeys the second law of thermodynamics. Entropy must increase in the universe. And so indeed, what we find is when we look at these isentropes, the isentropes become higher and the entropy states increase as you go, validating for us that, of course, it makes sense that we now have a higher entropy in this much more compressed state. So, as I mentioned before, since we now have ways of being able to actually measure the initial density, the shock velocity, and the particle velocity, we can start to solve for all of the other parameters. I should note that here I say UP equals U2. On the previous slide, it was U2 minus U1. This is assuming that you're starting at ambient conditions. So from this point, we can now ask ourselves, well, what exactly is the information that we can use to relate the shock and particle velocities? So in most materials, this takes a linear relationship that we can describe using this relatively simple formula, that the shock velocity is equal to C plus SUP. Unfortunately for our notation here, this S is not the entropy, but instead is a coefficient that we'll discuss in a little bit that's related to the isentropic bulk modulus at ambient conditions. This C here is related to the speed of sound in this material, also under ambient conditions. So ultimately we have this response here that we now can correlate the shock and particle velocities so long as we have these constants well defined. And we can see that the pressure is actually proportional to US times UP, which if we now plug in our equation for US, we see that's proportional to about the particle velocity squared. So our relations to describe kind of the constitutive behavior of materials that we would plug into our Hugonio is effectively now showing us this relationship that is indeed now material specific to describe the stiffness and compressibility of the material. So a highly compressible material like a gas versus a stiff material like a solid, especially something really hard like diamond, would have very different steepnesses of this type of line. The steeper the line, the stiffer the material. So ideally, we would find, as I mentioned before, that the speed of sound at ambient conditions, assuming this bulk modulus that I mentioned before, or the isentropic bulk modulus at ambient conditions, as I mentioned before, would be the value of C. And we would find that then, based on that, we would end up with the entropy, sorry, no, it's not entropy, the S term that we're using to define this constant here, taking this form here. Of course, it doesn't always work, and therefore this is often measured empirically instead of being measured or being predicted. But that's kind of something you can look into a little bit more in this Nellis Chapter 2 textbook if you're interested in getting into more details. So it's worth mentioning that the pressure and particle velocity are actually the only continuous variables that are continuous across the shock front. This is important because if we want to understand the relationship between shock waves as they go from one material to another material, we need something that doesn't have a discontinuity in it so that we can understand the behavior of those shock waves or the relationship between those thermodynamic states as they traverse the interface. So this now sets up for us the question of how exactly do we measure the shock velocity in, say, a material. Well, the Forbes textbook that I have down here has a beautiful chapter explaining how to do this. I will give you a kind of brief introduction to it to give you an overview to build your intuition, but I would definitely refer you guys to this chapter if you're interested in learning more or trying this yourself. So at an interface between two materials, that's here material 1 and 2, we find that the shock will both reflect back into material 1 and then transmit into material 2 once it reaches that interface. So we'll end up with something that looks like this, where S1, our initial shock, becomes now the superposition of S2 and S3 that are counter-propagating waves, where now S2 has increased in shock impedance. That's the slope of the Rayleigh line, which is the density times the shock velocity, whereas our S3 has now reduced in amplitude or in pressure. So what we can now relate these together and express them kind of for a bookkeeping notation here, using this what's called XT diagram. It shows us our initial shock, our reflected shock, and our transmitted shock, so that we can start to build our intuition for what's going on in this system. We can then look at the PUP curve over here, like we saw in the previous slide, and we can plot out our principal Hugonio for the forward shock in material number 1. In this case, I have a shock cartoon that is vaguely based on a foam material. And as I mentioned, we have this Rayleigh line that connects our initial to our shocked state that reaches the interface at point A. So now that we've gotten to this point, we have a shock impedance to define it. We have a pressure and a particle velocity. We now ask ourselves, well, what exactly is the character or the behavior of the other waves that we're considering in this system? Well, to answer that question, we now need to be able to understand the reflected shock in our material 1, which we now know must traverse through this point here that we denoted by S1 at P1 and U1, and also must be reflected so that we understand that the reflected shock has the opposite slope of the Hugonio, as all of the initial particle velocity is no longer at rest, but now traveling in one particular direction, i.e. against the direction of the shock wave itself. So this gives us this reflected one here, or Hugonio here, that we can see that is the orange dotted line. And we can then plot out our material 2. In this case, now we have a metal with a steeper curve here that is showing us the stiffer material. And this gives us the ability to now understand not just the state that we start at when we're reflecting, but also the state that we could go to based on the impedances in the new material. So this now takes us in S2 from our initial S1 that reached the interface to now the S2 that connects to the new dot on the reflected shock Hugonio that describes the P2 and U2 that are common across the interface between material 1 and 2. So this now gives us our second state to be able to understand how the behavior or the pressure and particle velocity have changed from the reflection and transmission. So, as I mentioned before, the reflected shock actually approximates an isentrope that describes the release path that we saw in a few slides ago, to be able to give us important information about what exactly we're observing here. So we can now ask ourselves, well, now that we understand how to study the shock wave, how to observe it, well, I guess we'll get to how to observe it in a little bit, but at least how to study and resolve the pressure in it. we can ask ourselves, what exactly are the behaviors that we would expect from these shock waves? Turns out the characteristics of the shock wave depend quite strongly on the strength of the shock wave or the magnitude of that shock wave. As you might expect in a nonlinear wave like a shock. So mechanical waves in solids, not just gases or liquids like what we've been discussing before, which is common across all those materials, these actually support shear loading, which means that when you compress in one direction, your material is resisting that compression along the off-axis directions. This very much can alter the compression path that the material will follow during shock. In solids, this means that, of course, there exists a strength of the material or the resistance to failure because the shear forces resist that deformation up to a point until the strength disappears. So if we start with a very gentle shock, we would end up with something that has the geometry shown here that we've seen in a few previous slides with a stable region or an initial jump, a stable region, and then a release following the compression. In this type of a single mode wave, we really are below what's called the Hugonio-elastic limit, at which point we would end up with a stress or pressure that actually would make the material fail. So in our Hugonio equation of state, what we see is that we have kind of a linear trend here that eventually reaches a kink point that then starts to bend, as we've seen in our previous slides. So as we increase the pressure now, we end up seeing something that looks a little bit more like this for our shock shape, as we have the initial jump reaching something that is near the Hugonio-elastic limit. Then we see some sort of a response following that, and a subsequent rise in pressure to reach our highest stable shock pressure that remains stable for a certain amount of time and then ultimately will release. There are all sorts of bumps and shapes in this that we'll get into in a future slide, but for now you can understand that this is effectively showing you the first wave as the elastic wave and the second as the plastic wave. At some point, though, we end up with a plastic wave that is not just slower, lagging behind the elastic wave, but actually overtakes that elastic wave. This is called the strong shock approximation, often an overdriven shock. And under these conditions, we really still see a single shock type of geometry, but now it's a single shock that is very much creating plasticity and damage in the material. So when we ask ourselves, what exactly is that behavior in the material that then follows, we find that there's something that looks quite a bit like this, that is a beautiful diagram that is used a lot in shock physics as kind of our introduction to how to think about material science during a shock. So we start with our ambient crystal here, and following this ambient crystal with a beautiful pristine lattice, in this case a cubic lattice, our initial shock is what's called a uniaxial shock along only one direction, as we see in yellow here, that is effectively a reversible wave that at some point, of course, becomes irreversible. We can say that effectively this wave is traveling so fast that it outruns the plasticity and failure of the material that would be required to see anything that is off axis from just uniaxial compression. But following that, at some point the shear wave does or is able to start catching up, and at that point we start to see things that look more like this, which is more of an more of a sorry, words are escaping me, more of a uniform isotropic compression. So when we get to the isotropic compression, now we have a picture of our material that looks more like this, where we have these shear forces that have caused the compression along all directions that introduce dislocations like this one, that are these linear defects or extra planes that are scrunched up in there. Or we can see other types of defects. There are many, many types of defects observed in shock physics. And subsequently, we can observe various different types of phase transformations and then release that follows. So to bring this back to the velocity or the velocity curves that we've been looking at before, this is what our Hugoniot-elastic limit would look like, and this is the equation that you can find in some of the literature based on the yield strength and Poisson ratio. Then we see this plastic flow type of a yield behavior that can cause, in ductile materials, can cause the material to actually now pull back in velocity as the plastic wave starts to catch up and starts to impose shear. Following that, we get our phase transformations and things that then follow the plasticity that occurs as we increase in pressure. And that ends up typically looking like a kink in our Hugonio, something like this. And at the highest pressure, we get to our stable Hugonio state that persists for some amount of time, till eventually we then start to have the spall behaviors that can go very, very long after we finish the shock process. So now we can ask ourselves, how exactly do we generate shock waves? Well, originally, historically, shock waves were generated by explosives. Big detonations or things like that would launch these massive blast waves that if you put your material in just the right spot, you could observe how the blast wave caused by the explosive, based on the power of the explosive, ultimately imparted specific types of pressure volume behaviors on the material itself. Of course, this was a little bit destructive, so we since have been able to come up with slightly more controlled ways of being able to study shock compression. It's also worth mentioning that, especially in this type of a geometry, these diverging versions of shock waves are actually decaying shocks, which impose slightly different conditions on the materials from our planar shocks that we discussed initially. So gas guns are some of the very commonly used versions of shock generation. In these cases, we have a piston, a metallic piston that is or projectile that's present in the beginning of our gun. It's held in place by a membrane. Then we fill in that region of the gas gun with a gas material until it breaches the membrane for the projectile, causing the projectile to then fly across the barrel into our target material that we have here, which we can then put various different probes on the back of to be able to study the shock response as the plate impactor reaches the impactor reaches the samples. Following that, there have been other types of shockwave generation that have been developed to be able to do other types of plate impact studies. One example of this is the Z machine at Sandia, which is a very, very massive machine that effectively uses a massive magnetic field to drive a current that then basically allows a flyer plate that is held on to this anode material to become loosened and freed very, very, very quickly, but launched off because it explosively flies off and therefore hits the sample, allowing us to generate our shock wave that we can study in the sample material based on the probes that are following it. In other cases, we have slightly smaller facilities that allow us to look at plate impact. There are laser-based versions of this that at much, much lower pressures are able to look at, say, a glass substrate with a metal foil on it. And then they can use a laser pulse to be able to, in a very, very small amount of time, generate a plasma that launches our flyer plate into or loose from the glass substrate and pushes it very quickly at high velocities into the sample material underneath. The advantage to a flyer plate method like this is that, of course, you can use tabletop lasers that are commercially available to be able to launch these types of plate compression material or shocks. And you can therefore have interesting types of spectroscopy or imaging that then can observe the types of responses in a much more careful way because, of course, you have much more access to the facilities. However, there are some challenges in being able to get a stable shock across the flyer plates and a stable plasma within the laser pulse itself. This brings us then to the final type of shocks that we'll be discussing today, and that is the laser-driven shockwave. So kind of going a step beyond what we saw in the flyer plates, if we instead of taking a smaller laser, take a massive, massive, powerful laser and focus it, and sometimes many beams of it, onto an ablator part of a material, what we find is that we can generate a plasma in that material that reflects back towards the pulsed laser. The plasma expanding backwards towards the laser then needs to obey conservation of momentum and launches a massive shock wave into the target so long as the plasma is sufficiently confined. So when we look at this, what we find is that we're able to therefore launch a really, really strong shock wave that can actually now start to give us these planar shocks so long as the spot is large enough. So now that we know how to make these shock waves, we ask ourselves, well, how exactly do we measure the dynamics that follow during shock compression? So as we've discussed quite a few times in this workshop, strong shock waves in solids always irreversibly change the material through mechanisms that are either called plasticity or inelastic failure mechanisms. So this necessitates that we do one of two things here. Either we need to call our measurements quasi-reproducible, and all the shot-to-shot variation that comes from, for example, when we have samples that are a little bit different, that have different defect structures, or that have slightly different drive conditions, we just attribute all of that to high uncertainty bars that therefore mean that we can assume our response is basically reproducible. This creates error bars that can make it very challenging to observe more subtle types of responses, but does actually make the experiments much more straightforward to understand how to relate to each other. But if we want to really compare the irreproducible and irreversible phenomena that are different, not just in different samples, but even if we were to cut in half exactly the same material, we find that we actually need to be able to collect all the information about the shock wave in a single shot or a single shock wave exhibited onto our sample. So this means that the measurement tools that we have for shock physics have been one of the biggest kind of enablers in our understanding of how shock waves transform materials. So we're now going to kind of ask ourselves for the rest of this workshop, how exactly do we measure shocked materials and what does that show us? The most established type of shock measurement that we can do is called a velocity interferometer system for any reflector. This is abbreviated VISAR, and it's a type of velocimetry that effectively allows us, using the interference of light against itself, to see a Doppler shift in light that is caused by the velocity of the back surface as the shock breaks out of the material. So this shows you one optical schematic from a Dan Dolan report from Sandia that is incredibly detailed about kind of the fundamentals of VISAR. For those of you getting into the field, I would urge you to read this report if you're starting to do VISAR, as it's incredibly informative. VISAR in general is creating an interferometer that allows us, as we can see from the Mark Myers book over here, to basically, based on a wavelength of light, be able to interfere the light with itself based on the displacement of a surface and how that displacement of the surface relates to the wavelength of the light that is being reflected off of it. So if the light reflects back and is exactly out of phase with itself, the light disappears and becomes opaque, so we see nothing reflected. Whereas if it just shifts a little bit, we end up seeing more of a beating pattern of the light, or it gets attenuated to some extent. This allows us to generate fringes that look something like this, where now we have the ability to see an even fringe spacing. But if we now have a moving surface that we're reflecting off of that's moving as a function of time, then we can end up seeing something that as a function of time allows us to see a bend in the fringes that correlates with the shift in position of the fringes as compared with a reference beam that we use to generate the fringe spacings here. So the free surface velocity measurements can be derived, and they end up taking the form like this, where based on the change in the fringe spacing, so the shift of the fringe, we can connect that back at any given point in time to the Etalon delay that is creating our reference sample to reference delay that generates our fringes. And there are a few different correction terms that are required to be able to account for things like a window that would be helpful in viewing the material but can change the refractive index, decrement, and therefore must be considered for the interference fringes. So this ultimately can give us a trace that looks something like this, where now we have the ability, as we've seen actually a few times already, to be able to see as a function of time, now based on our fringe spacings and how the fringes shifted and deflected based on the shock velocity and the free surface position, to be able to identify all the different information that we've been discussing about the material as it is first loaded to its elastic limit, then has some plastic flow, some phase transformations that may occur, reaches its Hugonio state, and then eventually decompresses in various different mechanisms and pathways, and can eventually spall once the release waves intersect each other and create regions of very, very large tension or extractive or expansive stress. It's also worth noting that as we measure Visar, the thickness of the sample matters quite a bit, as when we look at various different points of the wave traversing a material, we find that even if the pressure at the highest velocity or highest stress were to remain constant, in fact, the elastic wave does start to release a little bit as it travels. But indeed, shock waves also often decay a little bit. So if they end up decaying a little bit, we end up seeing something that looks like this, as we can see at the top. So this is a very important thing to understand when you're studying shock dynamics, as the behavior of a shock wave will be quite different, or that you observe in a shock wave will be quite different if you're looking at, say, 1 nanosecond after the shock has arrived versus you're looking at 100 nanoseconds after the shock has arrived, even for a stable shock that is that long in duration. So this then begs the question, well, how do we measure that response within the material beyond something that's kind of these more subtle bumps and variations in velocity that arise during the propagation of the shock through the material? So perhaps one of my favorite ways of doing this is using X-ray diffraction, which is one of the tools that we enjoy using here at Stanford and SLAC. That's the SLAC National Accelerator Lab, where we have a bunch of X-ray sources, including the LINAC coherent light source that allows us to do these types of X-ray diffraction experiments at really, really fast timescales, at timescales for which the atoms themselves actually stand still. allowing us to see some of these really extreme states of matter that we form during shock waves in ways that help us to decode some of the unusual behaviors of these shocked materials. So X-ray diffraction nominally takes this form of Bragg's law, where we can describe the wavelength of the light that is coming in and then is being reflected off the atoms themselves in the material, because X-rays have such small wavelengths that they are smaller than the atomic bond lengths, or at least high energy X-rays do, that we would use for X-ray diffraction. And then what we find is that at specific locations where we have atomic occupation, we end up having those X-rays be reflected. The reflected X-rays then come off. If they come in at an angle of theta, they come off at an angle of theta, giving us a factor of 2d sine theta to describe the spots that we get very, very, very far away after the reflected rays diffract, based on the infinite periodicity of this plane along the spacing of d between each plane. So what does this allow us to do? This allows us to, based on the patterns that we observe very, very far away, be able to get clues that tell us, based on all the relevant d spacings of the material and their orientations, to understand exactly what the atomic structure of the material is, averaged over the spot size that we're looking at. So X-rays are now starting to become used more and more to be able to map the structure of materials during shock compression. At some of the largest laser facilities in the world, like the National Ignition Facility at Lawrence Livermore National Laboratories, we have a few different types of systems that allow for X-ray diffraction using a backlighter that is effectively a way of simply shining a very powerful laser at a metal to generate a more broadband version of X-rays. And this allows us then to capture the diffraction patterns as arcs that look something like this. As I mentioned before, here at SLAC, we have the ability to shoot electrons with an electron gun to accelerate them through a particle accelerator, then to wiggle them back and forth to create coherent X-rays as a laser. We can then shoot into our experimental station to ultimately be able to probe the shocked materials. I should mention that this particular building that holds the National Ignition Facility is a very, very large, I think 3 to 5 story building at Livermore, not a small facility, with 192 beams. And this X-ray free electron laser here at SLAC is a 3 kilometer long laser that also is not such a small facility. So, although these are large facilities, they are facilities that are open to users that can then bring samples and sample stacks with ablators and windows mounted around them to be able to really study the behavior of the shock waves and how they compress and decompress the materials, and this type of what's called a pump probe geometry. So the optical laser pumps the material, generating a shock wave that is then probed at some delay time later by the LCLS free electron laser beam, i.e. our X-ray pulse that is so short in time that it allows us to directly watch the positions of the atoms as the process is evolving. So this was these types of experiments first started at the LCLS, so the free electron laser, in 2013, although they were done at the synchrotron before that, with lower brightness and therefore a little bit less time resolution, and has started to really change the way that we understand how materials fail during shock compression. Some really seminal studies have been able to demonstrate that actually, although normally we would expect materials would deform under classical conditions like the ones you and I live in, that we would expect that dislocations or line defects would typically be responsible for making metals deform. When we push them at 10 to the 9 per second strain rates, In fact, what we typically find is that they actually can't quite deform that way fast enough with enough energy. And therefore, they often start with twinning, which is a lower energy mechanism, before they actually start to then become dominated by slip or dislocations. Suffice it to say, what this has been able to demonstrate for us is the really subtle behaviors within the lattice of a crystal that during shock compression give us the ability to now see very new types of phenomena that weren't really accessible to us before we had these shock types of experiments, shock and diffraction. In other cases, we find that we can form very unique phases of matter that weren't actually accessible to us before, or that we maybe wouldn't have expected along a phase diagram. In those types of cases, we can watch now the diffraction peaks move and change to new locations, giving us a very clear view of the phase transition pathways responsible for that shock deformation. We can then go a step further, and we can even ask ourselves, what exactly beyond just the phase of the crystal in any little spot, how does this manifest as heterogeneous behavior of this material itself? So we can now actually also use microscopes, X-ray microscopes, to be able to zoom in and see things like our shock front that's propagating, the elastic front versus plastic front as they propagate, and to start to watch more subtle heterogeneous behaviors. Like, for example, if we do these things at the same time, we can start to see behaviors of phase transformations that happen sequentially, or different types of elastic versus plastic behaviors that would be incredibly difficult to be able to understand beyond simply understanding that a feature has evolved with our Visar measurements. So perhaps the place that will close in this important discussion of measurements during shock compression is the measurement of temperature. It's worth mentioning that measurement of temperature is something that, although there are many people that do, there's a lot of debate in the field still as to the validity of different types of temperature measurement approaches based on the characteristics and behaviors of the material, things like their reflectivity and such. We won't get into that today. We'll just give a kind of a broad overview of kind of the approaches that are used. So the Gruneisen parameter and the Gruneisen model is one approach or model that is used to describe how the Hugonio states I mentioned, or we started with at the beginning of this presentation, can be described to define the temperature of the system. We then can ask ourselves, well, how would we measure temperature? It turns out, of course, that black body radiation is incredibly helpful for this. So black body radiation is the reason why we see the sun as orange. It's the reason why when we turn on the burner on our kitchen stoves, at least for electric stoves, we end up seeing an orange glow once they heat up, as there's thermal emission that is a broadband emitter that has a central peak or point or color that shifts based on the peak temperature of the material. Now, black body radiation requires actually a three-dimensional view of the entire emitting material, which is not actually really possible because, of course, the material will reabsorb the light in various different places. The approach of, there are various different approaches that are used to interpret this, things like a gray body approximation or other forms of surface measurements, but ultimately, once we make these types of emissivity calibrations, we can plug this into Planck's law to be able to get the temperature based on the central wavelength of the thermal emissions. So although this approach has, as I mentioned, some limitations, it at least gives us a starting point to be able to understand at least an order of magnitude for where exactly we are in the temperature regimes. So this has been very helpful to understand how we're navigating phase diagrams, but of course has some limitations. There are new techniques being developed every day to try to understand shock compression, or the temperature behaviors of shock compression. There are new models being developed every day to understand the various different aspects of the material compression that can give rise to these types of heating effects. So before we close, I'll end this presentation with one final word about the sensitivity we have to remember whenever we do experiments on shock waves. So as we've discussed throughout this workshop, we have a very sensitive behavior in these nonlinear shock waves that make us very, very sensitive to sample variation. That's variation in the initial density of the material. So for example, if we were to 3D print a material and have pores throughout it, it would very drastically change the behavior of the material based on the porosity or based on things like the microstructure underneath it. We also, since we're looking at the transmission of pressure waves from one medium to another, at the very least when we generate our shock waves, but also when we observe them, we are incredibly sensitive to things like surface roughness and even more subtle things like the glue layers and thickness of those types of layers, as again, they create new interfaces that can create new impedances and new types of release pathways. Subsequently, we also then need to think about our internal defects and grain sizes, which can vastly change the types of deformation mechanisms that we have, changing the local pressure and temperature conditions, and therefore changing the shock response over much longer timescales. And finally, as we're putting all of these together, we need to think very carefully about ways that we can perfect our sample preparation schemes to make sure that we have samples that are as meaningful as possible for what we are trying to measure from the material. i.e., if we're trying to measure something that we know we need to have something that is comparable from shot to shot, variation is incredibly important to be able to quantify as precisely as possible. Whereas if we know that we're taking measurements where we have a lot of simultaneous probes that can calibrate for those things in situ, it may be a little bit less important, although, of course, it is still important to always know what you're shooting. So with that, thank you all very much for listening. It's been great talking with all of you about an introduction to shock waves and how they compress solid materials. And finally, I would like to acknowledge my postdoc, Dr. Sophie Parsons, for her contributions to these slides. And again, to thank Kamsky for their support and exciting science on additively manufactured, compositionally complex systems. Thank you.